So let's model the alternate segregation pattern starting from the same dihybrid that we were modeling previously. So in this case, instead of having them segregate like this, we're going to have these still segregate in this pattern, but these do the opposite segregation. So what that does is it brings this chromosome up here, and at the same time it brings this chromosome now, the one with the big B on it. And that's the one cell that forms after the meiosis I division. The second cell that forms has the little a alleles on it, and also has now the little b alleles on it. So that's the second cell that forms. And then as before, the meiosis II division is simply going to take each of these and separate what is attached at the centromeres. And this in turn will produce the following. So we will have big A, and then down here, little a, and little a. And then for the other chromosome, big B, little b, and little b. And then we could go and draw cell membranes around each of these to represent them as cells. So these are now the N or haploid products of meiosis. And you can see we have different allele combinations than we did previously because we now have the alternative segregation pattern. So for this particular meiosis, you'll notice that all the different products of meiosis are in fact recombinant. We didn't have big A and big B together as in either input packet. Similarly, we didn't have little a and little b together. So these are now all recombinant. So in the previous example, we had nothing but non-recombinants, and in this example, we have nothing but recombinants. Now, the overall recombination frequency for this dihybrid, if we're assuming that these loci are on separate chromosomes and assorting independently, again, you can draw out the different outputs that are possible, and we can label the ones that are recombinant. So that's recombinant, and these ones are non-recombinant. In the case of independent assortment, we've just drawn the meioses that produce the different possibilities, and they're equally probable because this is a 50-50 event depending on the segregation patterns. It's 50% chance of either possible pattern. So a summary of all the possible gametes that come out of this dihybrid in the case of independent assortment is to say, based on probabilities, that each of these have an equal probability. So if we were doing probabilities again like what we were doing before, we would say that each product of meiosis has a 1 in 4 probability. So then you might say, okay, well, what's the total recombination frequency when we have independent assortment going on? Well, as we mentioned before, recombination frequency is simply the number of recombinant gametes out of the total. And I should say products of meiosis instead of gametes. We tend to be sort of diploid-centric in this course because we're used to dealing with diploid genetics. So sometimes I'll say gametes when I really should be saying haploid products of meiosis. So in this case, the recombination frequency in this scenario, you'll notice that the recombinants and the non-recombinants are equal in frequency. So what this means is that the recombination frequency we could say is 1/4 plus 1/4 divided by 1/4 plus 1/4 plus 1/4 plus 1/4, or 1, which would give us a recombination frequency of 1/2, or 50%. So recombination frequency of 50% is another way to say that these loci are behaving as though they are genetically unlinked. And the reason why they are behaving as if they are genetically unlinked or genetically independent of one another is because they are physically unlinked. They're not physically on the same chromosome, and independent assortment is producing the pattern. In the next example, what we'll do is we'll put A and B on the same chromosome, draw the meiosis again, and show how now the probability of getting one gamete type, one allele at one locus is now not independent of what one gets at the other locus when they're physically together. So that's what we'll turn to in the next video.